Good morning, everyone. Let me start with a simple thought. Have you ever placed a metal spoon in a cup of hot tea and after a while found it uncomfortably hot to touch? That experience is your first encounter with heat. Now, what exactly is heat? Heat is not a substance you can bottle up or store. Instead, it is energy in transit. Whenever two bodies at different temperatures come in contact, heat flows from the hotter one to the colder one until both reach the same temperature. And remember, heat is always a transfer phenomenon. It doesn't exist in a body waiting to be used, it only exists while moving. In physics, we measure it in joules, while older experiments often used calories. So keep this in mind, when we talk about heat, we are talking about movement, not storage. Now let's clear up a confusion that often trips students, the difference between heat and temperature. Temperature is simply the measure of hotness. In fact, it is proportional to the average kinetic energy of molecules. A cup of steaming coffee at 90 degrees Celsius may feel hotter than a bucket of water at 40 degrees. But which one contains more heat? Surprisingly, it's the bucket. Why? Because heat depends not only on temperature, but also on the mass of substance and its specific heat capacity. This is why we use the formula Q equals mc delta T, where Q is heat energy, m is mass, C is specific heat, and delta T is change in temperature. So the next time you wonder why a swimming pool feels cooler yet holds enormous thermal energy compared to your hot coffee, you'll know why. Alright, let's quantify heat a little more precisely. Imagine you want to know how much heat a pan of water absorbed while boiling. Physics gives us a neat formula, Q equals mc delta T. Here, m is the mass of the substance, C is its specific heat capacity. That's how much heat is needed to raise 1 kilogram by 1 degree Celsius, and delta T is the change in temperature. Remember the sign convention, if a body absorbs heat, Q is positive. If it loses heat, Q is negative. This helps us track the direction of flow consistently. So measurement of heat is never random guesswork, it's based on mass, material, and change in temperature. Now let's zoom into the microscopic level. What is really happening when heat flows? At the particle level, heat is nothing but the transfer of random molecular motion. Molecules are constantly jiggling around, colliding with each other. The faster they move, the higher the temperature. The average kinetic energy per molecule can be expressed as E average equals 3 by 2 kBT. Here, Kb is Boltzmann's constant and T is the absolute temperature in Kelvin. So when you put a hot object in contact with a cold one, the faster molecules collide with slower ones, sharing their energy until everything evens out. In short, heat flow is the big picture effect of countless tiny collisions. Now the big question, how does heat actually travel from one place to another? There are three main methods: conduction, convection, and radiation. Conduction happens in solids. Think of that metal spoon in hot tea. The vibration of atoms at the hot end gradually passes energy down the spoon. Convection takes place in fluids. Imagine boiling water. The hot water at the bottom rises, cooler water sinks, and this circulation transfers heat. And then we have radiation, the only method that doesn't require any medium at all. This is how the sun's energy travels through millions of kilometers of empty space to warm our Earth. As you can see in the diagram, conduction is shown with energy arrows through a solid rod, convection with rising and sinking arrows in a liquid, and radiation with wavy arrows traveling through space. So remember, radiation can work through a vacuum, the other two cannot. Let's solve a numerical example to cement the idea. Suppose we have 200 grams of water, which is 0.2 kilograms, with a specific heat capacity of 4200 joules per kilogram per Kelvin. Its temperature rises by 30 degrees Celsius. We need to calculate the heat absorbed. We begin with our formula Q equals mc delta T. Substitute the values Q equals 0.2 multiplied by 4200 multiplied by 30. Multiply step by step. 0.2 times 4200 gives 840. Now, 840 times 30 equals 25,200. So, Q equals 25,200 joules. This large number shows why water is called a thermal reservoir. It absorbs and releases huge amounts of heat for small changes in temperature. That's why coastal regions with oceans have milder climates. Water moderates the heat. So, what have we learned today? Heat is not a thing but a process of energy transfer caused by temperature difference. Temperature measures the intensity of molecular motion, but heat measures the energy on the move. We quantify it with Q equals mc delta T. At the microscopic scale, it's all about molecular collisions and kinetic energy exchange. And in practice, heat can travel by conduction, convection, or radiation. So the next time you sip hot tea, swim in cool water, or bask in the sun's warmth, you'll know you're experiencing the remarkable journey of heat in action. I hope you now have a strong grasp of the concept of heat. In our next session, we'll explore how this energy leads to work and power in physical systems. See you there.